Alright, I'm gonna record another video for 114. Let's see. So, what we learned last time is that a current or a moving charge can create a magnetic field around it. Right? Very non-intuitive, but again, as I said, if you think about it, okay, very carefully, that's the only way to make a complete and consistent theory. So E&M, they're just one field. Now we call it E&M field, right? We don't really have electric field and magnetic field independent, okay? They're just components of the same field, right? So the only thing we need to create an electric field and magnetic field is just going to be a charge, electric charge, okay? So that's the only thing we need. We don't need any magnetic monopoles. Okay. So of course, if you want to, the theory for the magnetic field created by moving charge or current, very complicated. We saw these two equations last time, but as I said, we don't need to worry about these two equations. We're never going to use these two equations in this class. So all we need to do is just look at some very special, simple cases, okay? But they're still very non-intuitive, okay? So you do need to do a lot of practice. Watch the video, okay? Many times if you like, and do the homework, okay? Practice. So one thing we learned last time is that the magnetic field created by a straight wire, right? It's gonna be a bunch of circles around this wire, centered on this wire, okay? So if this is the conductor, it's connected to some battery, and it has a current going this way, say, and then it's going to create a magnetic field all around it, right? And then how do you find the magnetic field? You're going to grab the wire using your right hand, put your thumb in the direction of the current, your four fingers are in the direction of the magnetic field. So this guy, it's going to have magnetic field all around this way, not the other way, right? So one easy way to draw that, if you just draw a view from one end, like this, right? You saw this last time. You see I didn't even erase that. So you can draw the current, and then you can draw these circles on a piece of paper, okay? So that's how you find the magnetic field created by a straight wire. And the magnitude of this, okay? This equation is going to be given. You don't need to remember these fundamental equations, right? Then, as I said, a very special question, very classical question in this, and this is what the experiment we can do today to test the theory, right? If you put two parallel wires together, both of them carry current, don't have to be the same current, don't have to be in the same direction. And there's always a force, magnetic force between them, okay? Where does this magnetic force come from? Now you're going to use these two theories, okay, two right-hand rules to figure that out. This is where a lot of people get confused, because all the rules are called right-hand rules, and then everything is, you're going to use all the theories we have learned. This right-hand rule is the right-hand rule we learned at the very beginning of this part, right? So this is the same as that. This is a conclusion from this theory. There's a magnetic force on the moving charge always, right? So of course there will be a magnetic force on the current if it's placed in the magnetic field. And then when you use this right-hand rule, you do V toward B or I toward B, right? Because you want to find the force using the velocity of the charge or current of the charge and the magnetic field. You do V toward B or I toward B. But they're the same thing, because the direction of I is the same as the direction of the moving positive charge. This right-hand rule is that you have a wire there. There's no magnetic field. It creates its own magnetic field. You're going to grab that, okay? So you're going to grab the wire like this. It's out of the page. You grab the wire. Your thumb is in the direction of the current. Your four fingers are the direction of the circles, okay, magnetic field. They're both called right-hand rules, but they're different right-hand rules. This is misleading, a little bit very confusing for a lot of people. Again, practice, do a lot of practice, okay? So we discussed this last time, right? The key is that You pick one. Doesn't matter which one you pick. You pick one as the source. Use this theory to find out its magnetic field. And then we're not going to draw the circles. We're going to draw the whole wire and then draw dots and crosses to help us visualize the magnetic field. Why? Because using dots and crosses is easier for us if now I want to use the second theory to figure out the force from that magnetic field on that current. Right? If you use circles, it's very hard to do. So you draw dots and crosses, then you use these dots and crosses on the second current. Okay, doesn't matter which one you pick the first, right? You can pick this as a source, this is as the current, or this as the current, this as a source. Okay, all right. So now let's do the real problem on slide 15, lecture 13. Okay, so I'm going to erase this. Practice one more time. Now, 15, we still have two wires, parallel wires, right? You put them together. Then we want to find the force between these two wires. So there will be a force from I1 on I2. There will also be a force from I2 on 1, right? But they are action and reaction. You don't have to find both of them. You find one, then the other one, it's just going to be equal and opposite. Which law is that? Newton's third law. You see, we're still using the laws we learned in physics 1 because these laws are universal. Okay, so let's see. But the problem says find the force from 2 on 1. Okay, so we're going to find the direction on slide 15, and the magnitude on slide 16. Okay, so let's do this. First, find the direction. Again, always two steps, two theories. Let's do it one more time. Let's first draw it out. What do we have? I1 to the right, 40 amps, but we don't need the value for this part. And I2 also 40 amps in this direction. We call this guy I1, I2. Okay. Now, always two steps. You're going to pick a source, right? We want to find the force from I2 on I1. So that means I'm going to pick I2 as a source. I want to find the magnetic field created by I2. Okay. So I'm going to draw I2 first. Forget about I1. Okay, I2 is a conductor that carries current. It's going to create its own magnetic field. This theory, this new theory we just learned. Okay, how do I find the magnetic field created by this guy? This straight current. I'm going to grab the current, right? So use my right hand to grab this current. My thumb is in the direction of the current. My four fingers are in the direction of magnetic field. So I will see magnetic field going around it this way. But I don't want to draw these circles. First of all, they're hard to draw. Secondly, it doesn't help me to find a force. I will draw dots and crosses like what we did last time, right? So above I2, you see, you're going to see all these lines going into the page, right? So that means above I2, I would draw crosses. Because this is the magnetic field created by I2, right? I don't even interested in I1 now. Now below I2, you're going to see all these lines coming out, right, on this plane. Now I would draw dots. Okay, you can draw them as many as you like, right? But all the points above I2, it's going to be crosses. All the points below I2. So that's the magnetic field, right? Once you get used to it, it's easier than the circles, okay? All right, so now I'm going to place I1 in this region. Okay, I1 doesn't know, so I'm going to use a different theory. I1 doesn't know if I2 exists or not, right? I place I1 in this region. What does I1 feel, right? Now you can even erase I2, right? I don't even need this guy. I2 just feels, oh, there's a magnetic field around me into the page, right? So then we're going to use this theory we learned earlier. There's always a force from a magnetic field on a current, okay? From this theory, I, L crosses B. That's also called right-hand rule, but in this right-hand rule, you don't grab anything because there is a existing magnetic field. Now we call it B2 because it's created by I2, right? But again, in this part, I don't even need I2, right? If I just want to find direction, I already know this is the magnetic field I1 fuse, and I1 is above I2. So I1 fuse the magnetic field into the page. I1 doesn't feel this region, right? So, and also it doesn't matter how far away I1 is from I2. All the points above it into the page, right? Now I'm going to use this theory. I1 feels this magnetic field created by something. It doesn't even know, it doesn't even care, right? Now what is the direction of the force on I1? Now you're going to use this theory. Remember the direction of the L, even though we put an arrow on top of L, but this direction is the direction of the current, which is I1. Okay, you raise I2. I don't even need I2 now for the second part. So I1 is placed in the magnetic field called B2. How do you find the direction of the force on it? I toward B. I toward B. So okay, I1 feels the force up. That's a force from 2 on 1. Okay. All right, so that direction is up, right? So if I ask you, if you have done that, I ask you, then what is the direction of the force from I1 on I2? All right, let's just place it here. You can repeat the same process, right? Draw the magnetic field created by I1, dots and crosses, then place I2 in that region below I1 and do this right-hand rule. You will find the direction. Or you can just use Newton's third law, right? Action and reaction, okay? I2 has a force on I1. Doesn't matter if they're currents, magnetic force, electric force, action and reaction, they're still true, right? It's not only for pushing and pulling, okay? I2 has a force on I1 through some mechanism, okay? Doesn't care, I don't care. So I1 must have a force on I2 opposite in the opposite direction with the same number, right? So if I want me to draw the force from 1 on 2, it's going to be down on 2, okay? It's like A pushes B, B pushes A back. It's also true here, okay? So that's the direction. If you ask me force from 2 on 1, up. But if you also want me to find the force from 1 on 2, we're down on 2, okay? So that's this part. Now, the magnitude. Now we want to find the magnitude. The magnitude, you're going to combine these two theories to find the magnitude, right? So now let's see. At the first of all, I want to find the magnetic field B2, right? So I will use that theory, okay? Because that's the magnetic field I1 feels. Mu naught. Which do I use? I1 or I2? I'm finding the magnetic field created by I2. I'm using that theory. Has nothing to do with I1 yet. I2 divided by 2 pi d. Now the distance depends on where do you want me to calculate the magnetic field for you, right? But this is going to be the value of the magnetic field created by I2, okay? Now I'm going to use this B2 to calculate force on I1. So that's the second step. I just finished the first step. I found the magnetic field created by I2 around it using this theory. I haven't plugged numbers in, but this is the equation, right? Now I'm going to use the second theory to find a force on I1. If I want to find a force on I1, I'm going to use this theory. IL crosses B. When I use this theory, how do you find the magnitude? ILB sine theta, right? This is how you use the theory to find the magnitude. Now, okay, now I'm going to plug numbers in. Which I do I use? I1 or I2, okay? A lot of people, they will get confused. Which I do I use? The first is on which current? I1, right? And now you don't even care I2 anymore. I want to find a force on I1. I write I1 here. Right? I don't even care about I2 anymore. Which L do I use? Well, they have the same length, but you should use the length of I1 or I2. I1. I'm calculating the force on I1. I don't care about I2, okay, in this part. Now magnetic field is the magnetic field I1 feels, okay. Now you call it B2, that's fine. You call it B2, B3, B4, B0, B100, that's fine, right? But that's the number plug in. Okay, that's a number plug in. The magnetic field is created by I2. That's why I call it B2, right? But this equation, this theory, the second part, actually has nothing to do with I2. I'm calculating a force on I1 from existing magnetic field, and you tell me it's called B2. That's fine. That's going to be the magnetic field I plug in. Okay. Now sine theta angle. What is the angle? You need the angle between I and B. I is I1, B is into the page, right? So 90 degrees. Okay, now you can plug numbers in to find the value, right? I1 is here, okay? Now B2, now you can plug this in, okay? Because you don't know the magnetic field. You need to calculate the magnetic field. The problem doesn't say this guy is placed in the magnetic field with 0.5 Tesla, okay? I plug in 0.5 Tesla. It's different because it's not telling you the magnetic field. It just tells you the magnetic field is created by another current we call I2. And what is the theory to find that magnetic field? Well, I use this theory. That's the theory we learned, right? So I'm going to plug all these numbers in. Let's put all the symbols in first. 2 pi d sine 90. Now I'm ready to put all the numbers in, right? I1, 40 amps, right, from the problem. I2, 40 amps, right? In this case, they are the same, right? So even if you make a mistake, you will still get the same answer. But you may get a problem where I1 and I2 are not the same. So if you use a different, wrong current, you will get a wrong answer, okay? L1 is the length. Okay, they have the same length, 80 centimeters, plug them in. Distance, that's the distance between them, right? Because this guy creates a magnetic field around it. This D is the distance from the wire you want to calculate the magnetic field. I want the magnetic field in this region, along this line. So of course, this is going to be D I use, right? It's like if the line's here, that's the D I want to use, okay? So that's going to be the distance between these two guys, and that's 0.5 centimeters. So actually, they're very close, right? 0.5 centimeters, half a centimeter, very close, okay? So that's a D you use, right? And there you see that we have all the numbers we need. Now you can plug numbers in and find the answer. Mu naught is this constant, okay? So find this answer and then see if we get the same answer. All right, if you plug all the numbers in, 10 to the negative. So this is a very small force actually, right? See that 0.05 amp, okay, very small. And the current it's already very large, 40 amps, okay? So you have to put these two wires very close if you really want to do an experiment to test the force between them, right? And then if we can do an experiment to test the force between them, then we actually have confirmed this theory and this theory one more time, right? This theory we confirmed it last time, we verified it last time. And by setting up an experiment like this, remember we figure out the force using both of these two theories. So if we can do an experiment like that, we're gonna confirm these two theories. Okay, so that's what we're gonna do here, okay? So what we have here, this is a voltage source, and then I have one wire. I actually have only one wire, but I have this wire goes up and then turn around and goes down again back to the negative. So I can consider these two guys as two parallel wires, right? They're just carrying, you see that, the same current but in different opposite directions. So what did we just figure out? The force between them actually is going to be repulsive, right? So it's going to, they will feel a force pushing them away from each other if these two currents, they are in opposite directions. And this is true here, right? If the current goes up in one wire, then turns around and goes down in the other one, right? So that means if this is true, we should see these two wires pushing each other away, right? Okay. So again, let's try that. I'm going to turn it on. You believe in physics? That's how we test a theory, right? Do you do this experiment in your life? No. That's why it's very non-intuitive to you, right? But now let's do that. So I'm going to turn it on. Right? Do you see the force? Okay? They push each other away. Now I turn it off, no force at all. And I turn it on again, they're going to push each other away. Okay? Hopefully you can see that. Alright? I'm going to stop that. It's already getting very hard because the current is very large, right? You need a very large current to see the force because the force is still very weak between them. You have to put them very close, make the current very large so you can see the effect. Okay, so we have to confirm this theory. So this is also, this is a new theory we learned, right? The magnetic field created by a straight wire. Now, as I said, because we actually calculate this, okay, remember, if you really want to create a magnetic field using a straight wire carrying current, it's not very practical because you're going to have a ridiculous current to create a 1 Tesla magnetic field. So this is not what we're going to do in a real physics experiment, right? So as I said last time, there is a smarter way to create a magnetic field using a current, okay? So now we're gonna do that. So that's the second special case we want to learn this part, right? As I said, the theory is very complicated to calculate the magnetic field from a moving charge or a wire in general, but we only need to consider some special cases. The second case is the loop current, right? What is a loop current? Well, if you have like a wire, this guy is connected to some battery, and then you make a loop, that's a loop current, right? And why are we interested in this? Well, I will tell you the reason, okay, in a little bit. But first of all, let's first learn the theory. For loop current, you can also find out the magnitude and the direction of the magnetic field created by this guy, okay, using the very complicated theory I showed you last time, okay. But again, we're not going to do that here. We're just going to use the conclusion. So first of all, the direction, okay. And the magnetic field created by a loop, it's also very complicated, but we're only going to look at the magnetic field created by this loop on the axis of the loop. So if you take a look at the image on slide 17, okay, see the point P is on these on the axis of the loop, okay? So on the axis of the loop, okay? But if you want to pick another point not on the axis, it's still very complicated, but that's not what we're interested in this class. So the magnetic field at a point on the axis of the loop, the magnetic field, the direction is going to be perpendicular to the loop, okay? So how do we find the direction of the loop, the magnetic field? In this case, you're going to also grab this loop. You still use the right hand, it's still called right hand rule. You grab the loop, then your thumb is going to be the direction of the loop current. So I'm going to first draw this current direction for you. Okay, so that's that theory. Now it's a different theory now, because it's a loop current. A loop current is actually more intuitive than that, because once you draw it, you can see why it's more intuitive. Okay, so if there's a loop current, so there's a current going around it, right? So the magnetic field created by this guy is actually this way. Okay? And then, how do we find out the direction, right? So again, the loop current can go this way or that way, and these lines, they go that way, to the right or to the left. We still use right-hand rule. So you grab the loop this time. use your right hand, use your palm to grab the loop. So you're going to imagine you have a very big palm, like Hulk, okay? You grab the loop this way. You don't grab it this way, okay? Imagine you grab the whole loop, use your palm. Your 4 fingers now in the direction of the current. Okay, your 4 fingers in the direction of the current, because it's a circular loop, right? It's a circular current. If the current is going this way, I would grab it this way. So the magnetic field is going to be into the page, right? So if I rotate it 90 degrees, it's going to be this. The current going this way, okay, like this. So I would grab it this way, right hand. So the magnetic field is going this way. So that's how I would draw the magnetic field, okay? If you tell me the current is going the other way, I would grab it this way, right hand, and then you have to draw the arrows in the opposite direction, okay? So this is also called right-hand rule, but it's different than that. You still grab the loop current, okay? But now your 4 fingers are in the direction of the current. Your thumb is in the direction of the magnetic field. A straight wire, you grab the straight wire, your thumb is in the direction of the current. Your 4 fingers are in the direction of the magnetic field. So they're backwards, okay? It's a little bit confusing, but once you grab it, you know which is which, okay? Because one direction is circular, one direction is straight, right? For this guy, once you grab the wire this way, the current is straight. If the current is straight, you have to use your thumb for your current, right? Then the 4 fingers are the direction of the magnetic field, okay? Once you grab it, you know which is which, okay? And the loop current, how do you grab it? You're going to grab it this way. Remember, you always grab the whole loop. Once you grab the whole loop, you have to use your 4 fingers for the current. Now it's a circular current. You can't use your thumb for the current, right? See that once you grab it. So your thumb is the magnetic field. Your 4 fingers are the current. Okay, so sounds a little bit confusing, but once you get used to it, you grab the current, you know which is which. Okay, you know which is which. Okay, because one direction is circular, the other direction is straight. Okay, so that's how you find the direction. It's still called right-hand rule, but it's a little bit different than this. And these are the only 2 cases we need to know in this part. Okay, so that's the direction. Now the magnitude, okay, you have to derive it. So we're not going to derive it that here. We're only interested in the magnetic field on a point, at a point on the axis of the loop, right? So this magnetic field, it's a long equation. Again, you don't need to remember these equations. So that equation is on slide 18. Okay, so this can be derived, okay? We didn't derive that unless you want me to derive it. No, right? Okay. So what do these symbols mean? Mu naught is still the same constant. I is the current, right? So there's the current going around this loop. R is the radius of the loop, because this is a loop current, right? So this is the radius of the loop. D is the distance from the center to this point you want to evaluate. Right, so these are the symbols, right? And then if you want to find magnetic field at any point, this point, put numbers in. This point, put numbers in, right? It's going to get a different distance, but you just put numbers in. So that's only for the magnetic field along the axis through the center, right? If you pick this point, well, it's very complicated. This equation is not even true, but that's not what we're interested in this class, okay? So we're not going to worry about that, okay? So that's the second special case, a loop current, okay? That's the direction, right-hand rule, magnitude, this equation. The first special case we learned, a straight wire carries a current, direction, right-hand rule, magnetic field, magnitude of this equation, okay? And then when you use right-hand rule to find the magnetic field, you grab it. And once you grab it, you know which is which, right? One is the direction of the magnetic field, one is the direction of the current, okay? Once you grab it, your 4 fingers are always for the circular direction. Your thumb is always for the straight, okay? All right? So why is this more intuitive than that, right? Take a look at 19. You see that the magnetic field created by a loop it's very similar to the magnetic field created by this guy, right? So if I place this guy here, this is going to be the magnetic field created by it, right, from north to south. So you can imagine this guy, a loop current, pretty much like a bar magnet. So I would call this north pole, this south pole. So it's actually more intuitive than that, right? Because it's very similar to a bar magnet. It has a north pole and south pole. And this guy, it doesn't really have a definite north or south pole, okay? All right, so that's the second special case we want to know. And then now we're going to practice this theory, okay? This one, okay? Now let's take a look at slide 20. A circular loop of this guy, right? With the radius 0.5 meters carries a 4 amp current, okay? Along the axis at what distance from the center of the loop, it's 1/8 of the field magnitude as great as it is at the center, okay? It's a little bit long, the sentence, the question, really carefully. So basically, you want to find a point from the center of the loop, like say here. So you can calculate the magnetic field here, right? Let's call it P, BP. And then you want to find this point where this BP is only 1/8 of this, say this is O center, BO. Okay, so that's how you set it up. Okay, so now let's do that. Mu naught is still a constant. Okay, so basically you want to find a point P so that BP equals 1/8 B at point O, which is the center, right? So that's one. Now I'm just going to use this expression to write this BP and BO explicitly, and then rearrange this equation to find this distance, right? That's what we want to find. Now let's set it up. This guy, I'm going to just write this complete equation, IR squared 2D squared plus R squared 3 to the power of 3/2, right? Now the 1/8, that's the number, leave it here. Now the magnetic field at the point O, mu naught, it's still the same equation. At point O, what is D? 0, right? Okay, so you don't need this guy. It's going to 2 times R to the square and then to the power of 3/2. So you actually get R to the cube, R cubed at the bottom. Okay, now you're going to rearrange this equation, find D. Don't forget what we're doing. We want to find a D for this point P because you don't know where this P is. You want to find where it is. So this guy is going to be only 1/8 of the magnetic field at point O. So this looks very scary, but you can cancel a lot of things, right? You see that this denominator and this denominator, you don't need them, right? They are equal. So basically, you just want these two of the numerators, these two numerators equal. So basically, you just want this denominator equals this denominator on the right, right? Because they have the same numerator. I don't even need to care about that. So you just want these two guys to be equal. Now this is all math, right? Okay, now you see that we can even cancel this number 2 on both sides, right? So I would just get D squared plus R squared to the power of 3/2 equals 8R cubed. How do I solve this equation? Okay, I have this guy is cubed and then square root, right? I don't like square root in general. I'm not a big fan of square root. So whenever I see this, I would square both sides so I could get rid of this square root, right? So I'm gonna write this. So if I square both sides on the left hand side, I would just get D squared plus R squared cubed. And then you square right hand side, what do you get? You get 64R to the power of 6, right? Now what do? Well, I want to get rid of this cube here. How do you get rid of the cube? Well, I just take a cube root on both sides, right? If you take a cube root on both sides, so this is just going to give you d squared plus r squared on the left, right? It gets rid of this cube. Now on the left hand side, you're going to take a cube root on for both of them. This guy, you take a cube root, you get 4. This guy, take a cube root, you get r squared. Now you can finish the algebra, right? So finish the algebra, you can find the d, okay? And see if we can get the same answer. Move this term to the right, you get this. How do I find d? Well, take a square root of both sides. Right, so d equals square root of 3 times r. You see that the final answer is actually very simple, okay? That's what I usually say. Plug numbers in at the end, because you can cancel a lot of things, right, when you do the algebra. If you carry all the numbers here, well, it's going to be totally a mess. Now you can plug this r in, right? So you only need this r at the end. You don't even need the current or anything like that. The r is 0.5, so you put it in, you will get a d. Okay, so this number, this is a slide 20, this question. Now let's move on to the next part. Now calculate the magnitude of the magnetic field at this point. Okay, once you have this d, it wants you to calculate this BP. I just plug all the numbers in here, right? You see the r is already, now you're going to need all these numbers, okay? Or an easy way is this, right? Because I know this guy equals 1/8 of this guy on the right. You don't even need the d, you just calculate this number on the right? Because either way, it's going to be BP, okay? So plug numbers in and then find this magnetic field, okay? Do I need this? Okay. Now I'm going to erase this, okay? Because you have already seen it. All right, either way, if you want to find BP, right, you can either do this, okay, which is a little bit more algebra, or you can do this, right? So I'm just going to do this, the right-hand side. So it's going to be 1/8, right, mu naught. And this is even easy because r squared is going to cancel 2 powers of r here. It's going to be 2 times r. So it's actually going to be mu naught I divided by 16r. Okay? So you just put numbers in. Mu naught is given I. What is I? 4 amp, right? The radius, it's 0.5. You put all the numbers in, you will get a very small number, right? In the order of 10 to the negative 7th. Okay? All right, so we just practice this theory. So another reason I want to do this problem is this. Okay, this is another way to create a magnetic field in real life. But is this practical? Can I use this loop to create a magnetic field in real life? Say I want to create a magnetic field in an experiment, physics experiment. Well, it's still hard because you see that, what is the current we use? 4 amp. If you use a 4 amp current, you can create the magnetic field 10 to the negative 7. And this is too weak, right? This is too weak. This is even weaker than the magnetic field from the Earth. It's not going to do anything, right? Even the magnetic field from the Earth is going to dominate, okay? So, and then how do I use this to make a significant magnetic field in real life so I can use in physics experiment? One way is this, right? Okay, look at this equation. I would make the current very large, but that's not much you can do, right? Because first of all, increasing current is very hard. Secondly, when the current goes up, so it's gonna be more dangerous, right? And it's gonna melt these wires very soon, okay? Or you can make this d very small, but the d is, even if you calculate make the d at 0 at the center, it's just gonna be BO. It's just gonna be this number times 8, right? Still going to be a very small number. But there is a smarter way to make a significant magnetic field using this theory is this, right? What if I place another loop parallel to it and with the same direction of current like this? So this guy is going to create a magnetic field also in the same direction. So these two magnetic fields, they are in the same direction, they're going to add. What if I place a third one? Okay, so you would have 3 magnetic fields in the same direction, they will add. Okay. What if you place 100 of these loops together? So I'm not increasing the current, I'm just placing many loops together. So all these loops, make sure that they all have the current going this way. Okay, you don't have them going opposite way, otherwise they're going to cancel, right, the magnet. So all the magnetic fields they're going to add. So at the end, you will have a strong magnetic field, right? So that's how we do that. So we still make use of the loop current, but we make a lot of loops, put them together, so that you can get a very strong magnetic field. And you don't even need to use like separate loops. All you need to do. Now we go to lecture 14, slide 1, is that you make something called solenoid. So you just have a very long wire. A very long wire, now this is not long enough, but I just want to show you the idea. You wrap the wire on a cylinder, an iron core, so that so it's going to become many loops, right? So for example, this is a core. I'm going to wrap this guy on the cylinder, right? See that? Now I'm just making many loop currents. And another nice thing is this. If you do this, all these loops, single loops, they're going to have the current in the same direction, because that's what you want, right? You want all these loop currents in the same direction, so the magnetic field adds. And then imagine the current is going from this side to my right hand, okay? I don't know if you, in the video, which hand you can see which hand is which. But okay, it's coming to this hand. Now if I wrap one loop on it, you see that on your side you will see the loop current down, right? Going down to my hand. Now I wrap another loop. So the second loop, what is the direction of current? It's still going down on your side if you look at it. The same direction, still going down because my hand is here. Still going down, right? So if you wrap the same wire on the iron core and a cylinder, all these loops, like you put them very close together, so you can wrap, if you have a very long wire, you can wrap like 1,000 loops on it, and it's very easy to do that, right? So all these magnetic fields, they're going to add, so at the end you will create a very strong magnetic field. So that's how we use electric current to create a magnetic field in real life. We call this thing solenoids. So I do have some solenoids here. You see this is a solenoid. Wrap one wire on this guy very closely, so they're like, this is already like hundreds of loops, I guess. And this is also a solenoid, right? So one single wire, very long wire wrapped on it, many loops very close to each other, so they will create a very strong magnetic field. This also a solenoid, okay? So that's how we create a magnetic field, strong magnetic field in real life using a current. And then an ideal solenoid, so let's take a look at slide 2. An ideal solenoid is a solenoid where the turns are very closed. So these are already very closed, right? And the length is much greater than the radius of each turn. For example, this guy, right? It's very, well, it doesn't have to be a circle, right? Rectangle is fine, right? As long as it's wrapped on the same core. And then in that case, the magnetic field, if you take a look at the magnetic field on slide 2, you can see the magnetic field outside the solenoid is going to be very weak. But the magnetic field lines on the inside the solenoid, they're very close to each other, right? So it's going to be very strong. So the magnetic field inside the solenoid is going to be very strong. Outside is very weak, almost zero, okay? So now a solenoid is very similar to a bar magnet, right? It's very similar. It's going to have a north and south, okay? So then In real life, we use a solenoid to create magnetic field, a very strong magnetic field, okay? And we make use of magnetic field inside the solenoid because as we just saw, the magnetic field inside the solenoid is going to be very, very strong, right, compared to the magnetic field outside, okay? And it's going to be very uniform. You can look at the lines inside the solenoid. Very, very, almost parallel to each other. So very uniform, okay? And then how do you, how do you use this magnetic field? You definitely need to know the direction and the magnitude, right? Direction is the same as this loop. Because this is still a bunch of loops and with the current in the same direction. So it's just grab the solenoid like you grab a loop, right? You grab a solenoid, your forefinger is in the direction of the current, if the current is going this way, and your thumb is the direction of the magnetic field, right? So in this case, it's also the North Pole, where the North Pole is, right? You see that? Take a look at the image on slide 3, okay? So the direction, the same right-hand rule for a loop current, right? Because this is nothing but a lot of loops wrapped together. And the magnitude, so you don't have to use this equation, because this is only for one single loop. So it can be derived for solenoid. It's actually going to be a very, very easy equation, very simple equation, simpler than this, right? See that? So that's why solenoid is very useful. So for a solenoid, the equation is this. Mu naught still the same constant. And then this big N is the number of the turns, which can be a very large number, right? And then divided by L. L is the length of the solenoid, is this length, okay? Not the length of the wire, the length of the solenoid, the cylinder, okay? And then I is the current. So that's the single, you only have one current here, right? Because this is one wire, very long wire wrapped on a core. So you still have one I, right? So that's how you calculate. This is only for a solenoid. You only use this for a solenoid, okay? And sometimes you may see this notation. They call this guy, because this is going to be a constant, a property of this solenoid, right? Because the total number of turns divided by the total length is just the number of turns per unit length, right? So this is going to be a constant for one solenoid. So usually you will see this notation. Some books just write this thing, replace this thing with a little n and call this number of turns per unit length, okay? But that's just a notation, all right? So, and then as I said, the solenoid, we use solenoid to create a magnetic field in real life because then you can create a very large magnetic field, right? Because the N, you can make it the N very large, right? Thousands of loops, right? So one application of this is the MRI scanner, okay? If you have seen MRI scanner in a hospital or in a movie or something, you can see the patient is always being sent into a cylinder. And that cylinder is a solenoid, okay? So basically it's something like this. The patient is being sent in. And then because the magnetic field inside the solenoid is very strong, so that's the magnetic field we use to generate images of the organs in the body, okay? What does this M stand for in MRI machine? Magnetic, right? Okay? And many of you are going to become doctors in future, so you will, I guess some of you are going to work with the MRI machine, right? So this is one important application of this solenoid, okay? And then the majority of the MRI machine, they operate at 1.5 Tesla. As I said, 1 Tesla is already a very strong magnetic field. It's very hard to create 1 Tesla magnetic field. So that's why these guys are very expensive, right? And then it uses a solenoid, okay? Okay, so let's summarize what we learned so far on slide 5. So to create a uniform magnetic field, we use solenoid, right? To create a uniform electric field, we use parallel plates. And then that's how we create uniform electric field and uniform magnetic field in a real physics experiment, right? If you want to do an experiment, of course you want to create some simple, easy electromagnetic field, and then you study the behavior of some elementary particles in these fields, right? You're not going to create a crazy, ridiculous electric field or magnetic field, right? There are already a lot of parameters in that scale. So how do we create a uniform electric field, magnetic field, parallel plate? We already learned that. That's how we create a uniform electric field. How do we create a uniform magnetic field in real life, especially in a physics experiment? We use a solenoid. And you can take a look at the image on slide 5 at the bottom. That's a solenoid used to observe the LHC, the Large Hadron Collider in Europe. Okay, it's a very huge collider. Okay, and then you can see how large it is, right? There are some people standing there underneath this solenoid. You can see how large it is. That's how we create a uniform magnetic field in real life. All right, so I'm gonna stop here and take a break. Okay, I realized in one lecture I was doing this demo with this parallel wires. The camcorder didn't get it, so I'm gonna record a very short video for this demo. So in this lecture, we solved the problem with 2 parallel wires, right, with opposite currents. Our conclusion is that there will be a force between them pushing them away from each other, right? Repulsive force, very interesting, because of this magnetic field created by one wire, and then the magnetic field has a force on the other wire. Okay, so this is a demo, right? I have one wire. Actually, I have one wire connected to the source, but this wire goes up and then turns around at the top and then goes down. So if you consider them as 2 wires, then the current in each wire, they're just going to be opposite, one up and one down. So the force, if I turn this on, the force between them is going to be repulsive. They will push each other away. You should see that force. Okay, now I'm going to turn it on. Okay, I'm going to pick a voltage. Now you see the force between them, pushing them away from each other. I turn it off, nothing, and then I turn it on again. They push each other away from okay. Turn it off, nothing. Okay, hopefully you can see this this time.